Okay, hello everyone, and today we're going to be looking at using the normalcdf function to calculate some z-score based data concepts in statistics. So you may remember my last video on z-scores. It's going to build slightly off of some of the knowledge we learnt from there. However, we're going to be looking at the probability of a random variable within a normal distribution, where it could be located. What would be the likelihood of a random variable being within a given interval? And that's essentially what normalcdf does. A few things to point out. I will be using a calculator. This is going to be a very technology-based concept because you need to be able to use a calculator effectively and be able to understand the conceptual side of the questions in order to get a proper solution. So, just pointing out a few things. My next video will be on quantiles, k-values, and we'll look at them a bit later. But again, normalcdf today, so hopefully you've seen the previous videos to get a little bit of an understanding. So, a CDF, you're probably wondering, it's a cumulative distribution function. And again, it's to find the probability of a random variable and the likelihood of it being within a specified interval. And that's based on values of mu and sigma, which are generally given or we can calculate in some way. Because again, mu is important because it gives us a mean, the average point, and then sigma, the standard deviation, is important because it gives us a representation of the spread of values. Just like variance as well, but again, standard deviation more common, especially for this kind of level. So now lastly, something I did want to point out in the last video, but I didn't quite get round to in the second part, was a standard normal distribution. Standard normal distribution simply means that mu equals 0, and a standard deviation equals 1. So if we're to look at the standard deviation above the mean, that would be a position 1. And again, that's sort of like z-scores when we think about it too, because that's a measure of standard deviations. So that's something to add to your vocabulary. Again, if you have a notepad, maybe you want to take some of the notes of what I've got on the board here, because this is some of the conceptual stuff. But again, standard normal distributions can help if we don't have a mu or a sigma value. We just substitute in as being 0 and 1 if we're just looking for probabilities based around z-scores, which we're going to do now. Okay, so what I'm going to do is I'm going to draw up a normal distribution. And for the first set of problems, we're going to be looking at the standard normal distribution, where mu equals 0 and sigma equals 1. Okay, so we've got a nice clear space here. And let me draw up the distribution. So it's going to look something like that. We're going to have mu, then we're going to have mu plus sigma, mu plus 2 sigma, and then eventually mu plus 3 sigma. And then again, the other way, we're going to have mu take sigma, mu take 2 sigma. And again, this is very rough and it's not to scale, but it gets you an overall good idea of what's happening. And that's the most important thing. So now, what we want to look at is the likelihood of a random variable being between this interval here. Negative 0.41, less than mu, less than, and I'll go 0.67, which is also equal to 2/3. So we want to find the probability of a variable in that interval. And again, we're assuming, because this is a normal standard distribution, that mu is 0 and sigma is equal to 1. Well, just by looking at this, we can see that it's not going to be out here somewhere. It's going to be around about there that we're looking at. 2/3 of a standard distribution to the right, because again, that's positive. And our lower limit, negative 0.41, would probably be somewhere there, just under half. So we're looking for the likelihood of a random variable on this distribution being within there, between the z-score of 0.41 and the negative 0.41, sorry, and the z-score of 0.67. So in order to do this, and I will go through instructions for the TI-84 calculator. Sorry if you own a different calculator, just post in the comments below, and I will give you some instructions if you want, but I don't really have enough time to be able to give instructions for both. Again, the basic pattern's up here for a TI-84. So we go second function, and then we go to vars, and because it's on the second function, it becomes distribute. And then we go down to normal CDF, and depending on what values you calculated using normal CDF before, the mu and sigma may be different, but you want mu and sigma, again, you can navigate using the arrow keys, but you want mu and sigma to be 0 and 1. The lower we want to be negative 0.41, and we want the upper to be 0.67. So once you've entered those details, again, it depends on whether you have the old ROM or the new ROM as well. If you have the old ROM, you want to put in your lower limit, which is negative 0.41, then your upper limit of 0.67, then mu, which is 0, and standard deviation, which is 1. But if you have the new ROM, then where it says lower, you should have that value next to it. Where it says upper, you should have that value next to it. Then you should have mu, and then you should have sigma. Then click paste or press enter, depending on which one you get. And you should have this value here. The probability is going to be equal to 0.4077. And again, essentially that value there tells us what is the probability of a variable being there. And as you can see, it's just under half, essentially, because if it was 0.5, then it was going to be half of the distribution would be covered there, half of the probability of any value there. It's essentially giving us the area under the curve, assuming that the entire area under the curve is 1, then it's giving us the portion of the curve which is 0.40, which is where our variable will be. So again, if we were to write this out properly, the question would probably ask the probability of that, and it would probably actually, say z in here rather than mu, again z, because that's our random variable, rather than just having the mean in there. Again, I apologise for any confusion there, but let's move on to the next question. And this one's quite an interesting one in my opinion. It asks us what the probability of having a variable greater than 4 standard deviations away from the mean is. And if you know anything, then you'd know that from 3 standard deviations onward, we would have 0.15%. So it's quite a low probability of a variable being out that far, but it's quite interesting to see how quickly the actual thing fades off. So I'll add that there, just for the purpose of this question, and ask for the probability of variable z being greater than or equal to 4 standard deviations away from the mean. So again, similar thing. We go into second function distribute, normal CDF. Our lower limit this time is going to have to be 4, and our upper limit is going to be the maximum our calculator can handle, because our calculator can't have infinity there. So this value is going to be e to the power of 99. That's the maximum value that a calculator can handle. So you plug in e, and in order to do that, you go second function, and then the double E button, which is the comma button. And again, you want the mean to be 0, and you want the standard deviation to be 1. And then you want to click paste. Again, because we're working with a standard distribution here. And as you can see, the figure is incredibly minute. The probability of that actually being more than 4 standard deviations away from the mean, so somewhere there, the probability is equal to 3.17 times 10 to the negative 5. So if you understand scientific notation, you get an appreciation of how incredibly small the probability of something being that far out would actually be. So again, you can think of that as being something like someone who does really well on tests, they exceed the rest of the group or something like that, or you could think of it as being a significant outlier for the weight of a tin can. Maybe there's like heaps and heaps of tuna or spaghetti in one tin can, a lot more than all the others. Again, it's a significant outlier, and that's why there's a very small probability that a value will lie there, a randomly distributed value. But again, that probability is not equal to 0, even though it's 4 standard deviations away. So we get an idea of how the bell curve actually fades out and how it keeps on going. I mean, we could look at 5 standard deviations, 6 standard deviations, or even 7 standard deviations as well, and we get quite an interesting pattern. So now let's have a look at another one. And for this one, we're going to have a look at the probability of a z-value being less than or equal to 1.2. So this essentially says the z-score of 1.2, what is the likelihood of a value being less than that? So if we were to draw this up here, it'd probably be about there, and of course it would be to the left because it would be less than that. So what is the probability of a variable lying there? So in order to do this, we need to go into normal CDF. So second function distribute, normal CDF, and then we need to plug in the lower limit, and the lower limit is best defined as negative e to the power of 99. So because of that, we need to go to our calculators, and after we've typed in the lower as being second function negative, oh sorry, not second function, just negative, second function e to the power of 99, then we need to do our upper as 1.2 and keep our mean and standard deviation on 1. After we've done that, we just click paste and we get an answer. And again, it should be a decent chunk of the distribution because, as you can see here, it's all of the left side and part into the right side. So you know it's going to be greater than 50%. It's always important to check your answers and see if something's way off, then obviously don't write it down. Think about where it could have gone wrong. But in this case, we do get the correct value if you've plugged it incorrectly. Again, this is the lower, 1.2 is the upper, the mean is of course 0 and sigma is 1. So we get a probability of 0.885. And you know, that's a pretty decent probability. It's very likely for a random variable to be within that interval. Okay, so now I want to introduce you into the concept of how standard deviations and normal distributions are actually notated. So let's have a look at this. Let's say we had a distribution and it was represented by n73 squared. This is a general form for representing a distribution, by the way, and what this actually means is it's a normal distribution, and that's the mean, so the mean is of course going to be 70, and this here is the standard deviation squared. So from that we know that the standard deviation equals 3. And again, that's just another way of representing a normal distribution. So let's say we had that distribution and we wanted to know what the probability of a random variable lying in this interval here would be. So again, just I'm using, in fact I'll probably use x. X as our random variable, and go to 68.4. So in order to do this, I'll write up the calculator instructions again, so hopefully you get the hang of it. But if we go into our T84, and if you have the new ROM, then your upper, in fact it starts with lower, sorry. So we start with our lower, again, second function distribute. Lower would be 60.6. Upper would be 68.4. Mu, the mean, would be, and we had it up before, it was 70. And sigma is equal to 3. And again, if you have the old ROM, it would look very similar. It would just be in brackets 60.6, 68.4, 70, and then 3. So the probability, when we actually plug this into our calculator and work it out, 60.6, 68.4, 70 and 70, 70 and just 3, get paste, and the probability is going to be equal to 0.296. And again, that essentially tells us what the likelihood of a variable being in that interval would be. So again, it's very useful for normal CDF on a calculator because it can give us an idea of whether it's likely for someone to be at a certain height or whether it's likely for a can to have that certain mass. It gives us an idea of working out the interval in terms of a probability. So normal CDF's really good. There'll be part 2 to this where I'll look at some more conceptual problems. Hopefully I introduced this topic reasonably well. If there's any questions, please put them below. But again, yeah, it's an interesting thing to look at and it can be really helpful in statistics. Thank you, and see you in part 2.